will become important as the universe expands. Now, as the universe expands, you form a lot of strings, but the long string will chop up loops, and the loops will have gravitational radiation, and then they will sort of decay themselves. So that it doesn't really behave like this, but rather behave like one of a cube during matter-dominated era, and like one of a fourth like radiation era. And as a result, it will produce the fraction of energy content in the universe. If there's cosmic strings, then you will go more like a constant, which is g mu, g, Newton constant, mu, the tension of the strings, and gamma is a factor that is done by some numerical work, analytical work, roughly is on order of 50. So this is still very, very small because g mu, we talk about 10 to the minus 6 is ruled out, so it must be smaller than 10 to the minus 6, and so the energy content in a cosmic string is negligible as far as we can tell, compared with dark matter, and dark energy. Now, the present observational bound coming from pulsar timing. That's a very, very well studied. The bound keep improving. Is roughly g mu smaller than 10 to the minus 9. And remember, to produce the density fluctuation has to be 10 to the minus 6, which will be wrong. So now it will have play no role in the density fluctuation for structure formation. Now, it's also pointed out by a number of people that if you have a cosmic string, it will evolve, and as it evolves, it will oscillate, vibrate, and at the same time, cusp, which means that two parts of the string will end at a single point, which move at speed of light, and kinks, which will move around the strings. They will be produced on a regular basis, or will stay there going around the string as the string evolves. A generic string will produce cusps and kinks. How many we don't know, but typically we assume about 1 per string group for cusp. Now, as the cusp is formed, it will radiate gravitational wave in what we observe would be like a burst. Okay, so burst will go like this. It will be some magnitude, and then it will go to 0 and come back up. Because when we directly hit it, then the wave burst will go to 0, come back. So you take this form t to the 1/3, and this is rather peculiar than the waveform, a good signature for cusp. And kink will have similar, but this t to the 2/3. So these will be very distinct signature for gravitational wave bursts arriving in detectors. Not as spectacular as binary black hole merging, which we will go through a long period. This will happen like an instant, unless of course the string loop is small enough, then it will repeat itself. Now, so let me now go to string theory. We all know that string theory tells us the most elementary objects will be just nothing but modes of string theory, ground state modes typically. And string theory has 9 spatial dimensions. And so what we do is that we consider 3 of the spatial dimensions to be large. Essentially, there's 3 spatial dimensions we live in, which span the universe observable part. And the other 6 dimensions are compactified in some manifold. And so with this picture, string theory has been studied extensively for many years now. And cosmic superstring was first proposed in 1985 in the context of heterotic string theory. But as he pointed out himself, the tension would be g mu 10 to the minus 3, which is way, way too big. And also, they are not stable. So that means that cosmic string coming from heterotic string cannot be present in our universe. However, later on in the 1990s, the brain's presence was brought in by Kuczynski and others. And then the brain wave scenario appears. And in that picture, we can easily see now we can have cosmic superstrings. And they actually can be present in the early universe after inflation, and they can be consistent with observations. For reasons that I explained in a moment, the tension is typically lower than the present back. And they will have different properties, which I'm going to go through some of them. And so this is where, in the summary I said, is that they offer the best choice. I would also like to combine this with microlensing, which will offer in a way which is using electromagnetic wave to detect it. So the picture we have nowadays is roughly the following. We have brains, like say D3 brains, which brains span three-dimensional space. Here I display two. We, out of galaxy, everything, audio matter sort of lives in it. And then there's 6 dimensions, which is perpendicular to this, which is replaced by 1. So this is the brainwave picture. If I try to plot it another way, the 3-dimensional universe we live in are points here in this supposedly 6-dimensional manifold picture. But this compactification turnout is involved flux compactification, which involves warp geometry. For those who are familiar with Randall syndrome, this is a more sort of intricate, non-trivial version. That is, instead of 1 extra dimension, which warp 6 dimensions of warp, all 6. So what happened in this geometry, besides some cycles, there are throats. I'll call throats. I draw 4 down here. And throats essentially means that there's 6-dimensional space connected by the bulk, and the geometry is warped in the sense the mass scale at the bottom of throats are substantially lower than the typical scale of string theory here. And for the purpose of this discussion, I will consider string theory scale to be around gut scale. Okay. So that's, roughly speaking, is about 10 to the 16 or 10 to 15 GeV, that scale. You can, of course, move that up and down somewhat, but it's not going to change the picture. And also that what happened, of course, in early universe, we can have brains. These are D3 brains, but point-like, can be moved around. And then we can also some anti-brains, which are different color. And because brains have charge, and you can anti-charge, so both has tension, but they can have opposite charge. So this is roughly the picture that nowadays when we try to construct models, hopefully contain our standard model, this is the picture that emerges. In this picture, the geometry becomes very complicated. Here I draw 4 throats, but typical compactification can have dozens or maybe even hundreds of throats. So we can see that it's very involved. And you can have a lot of brains, and I also skip about the possibility of 7 brains, but generically we have brains, D3 brains, which as they move down the throat, that's where they're attracted by the anti-brain. So brain-anti-brain tension can drive inflation. This is the brain inflation picture. And then when they collide, they annihilate each other, and the brain tension, which provide the vacuum energy for inflation, will be released, and that energy release will heat up the universe, and at the same time they produce a lot of closed rings, and some are small, some are big. Some of the big ones become cosmic superstrings. So that's the picture. In this picture, there's another important point, is that there's no zero-point objects or two-dimensional objects. There is no point-out object like monopole, because there's no D0 brain. And there's no objects like 2 brains, like membrane, like domain walls. So the only object we have is odd-dimensional objects, like D3 brains, and the 3 means the 3 spatial dimensions. And they have D1 brains, which can be 1-dimensional, like strings. So D1 branes can be strings in addition to fundamental strings in the system. So there will be two kinds of one-dimensional objects that naturally emerges from this picture. Now, I'm not going to go through all the different properties, but I'll roughly give you some idea in which way things are different. Okay? So typical, as I said, there can be many throats, and we are probably a stack of D3 branes living in one of the throats. Okay? So we call it standard model throat. And the properties of that throat with what kind of branes we have and what kind of physics we have. At this moment, we can produce something very similar to our standard model, but so far nobody has come up with one that precisely matches our standard model. But there's many, many possibilities, and so people have studied that in detail. But as I said, if you sit at the bottom of a throat, okay, then there's a Y factor, and the Y factor means that the same D3 brane or D1 brane or string sitting in the bulk with some tension. As you go down there, the tension will drop, okay, by the Y factor. So each throat will have its own Y factor, and typical Y factor is much smaller than 1. And that's very important. That's why we call it throat. And that's the reason why D3 branes sit at the bottom of the throat, and why anti-D3 brane will flow to the bottom of the throat as well. So, with the D1 brane, we call D strings, and with fundamental strings, we call F strings. Together, they can form what we call cosmic superstrings. Now, strings in the bulk, we have tension G mu roughly order 10 to the minus 6. That's if you sit in the bulk. Bulk means that where there's no warping, typically, but the throats are all connected to the bulk. That's the picture we have. And at the bottom of the throat, the effective G mu is the G times M string squared times the Y factor square. And Y factor square is smaller than 1. And so the tension of the typical cosmic string can be orders of magnitude smaller than the present bound. That can be just below it. And from that point of view, we can easily argue why so far observational bound can be satisfied easily in this picture. Now, this is a technical detail. We don't have to go into detail, but let me just explain to you one very different properties, and that is that D strings and F strings can form bound states. Okay? And in forming bound states, you can have junctions, and in the particular geometry we have, you can actually work out in one geometry that be well studied in particular flows, and you can work out the tension spectrum. There's a whole spectrum of different tensions coming from the bound states of D strings and F strings. And at the junction, they can have a beat, or we can, in terms of gauge theory, baryons. And so these allow us a much richer cosmic superstring spectrum than cosmic string, which have one single tension. That's people have said before. So now, they form, for example, if I have two strings intersect, okay, we call interconnect. They can reconnect this way to form a bound state, or form bound state this. And the picture I draw is that all these are either very infinite long strings or strings from a big loop. I just didn't draw the rest of the strings, but they can form bound states, and then you can easily see that 2, 3, 4, they can form bound states of different tensions. Okay? And this can zip up and down as the system evolves, so the picture can be very rich and non-trivial. This is clearly a property of cosmic superstrings. The other very important property is that in vortices that people have studied before, when a string interact, for example, a string form a loop, and then the loop will chop off, and this we call intercommutation or reconnection, and the probability for vortices, the probability of this is 1. But for string theory, remember the interaction is G string, which is typically maybe 1/3 or 1/10. So the typical probability of this happening is substantially smaller, and it depends on how fast they move towards each other, what type of string touching, and what angle they touch. And typically the probability of intercommutation is, can be as small as 10⁻³ . And the smallness of this enhances the energy density in the cosmic strings by a factor, maybe 1/p or 1/p to the 2/3, depends on the different error. So this will enhance the density by 1 or 2 order of magnitude. Okay, so what we have now, we find the warping factor lowers the tension. So in fact, we don't know what the lower bound is, but certainly lower than 10⁻⁸. But at many throats, each throat has its own tension spectrum, and each throat has its own scaling cosmic string network evolved independent of other throats through the leading approximation. Now, we also say that there are multiple throats. Each throat has its own, and each throat has a spectrum. So again, instead of compared with ordinary cosmic string, we get a factor of maybe 1 to 10 improvement, 10 to 100 improvement. And so together, plus the intercommutation probability, we find that the energy density in the superstring, cosmic superstring, can be one factor, curly G, bigger than ordinary string. So that's a factor that we find different. And that factor can be as big as 10⁻³. So this enhancement is what's one of the elements that allow us to detect it where we compare with cosmic strings itself. So this essentially tells you what happens if we have different type of string, how it evolve. If you produce a lot, the solid line, a lot, and then one particular type string here is a single F string, you produce a little bit, and then they will evolve and approach a scaling solution. So this is all the strings. This is one particular string, F string. And then the dash curve the same thing. Initially we produce very little, and then evolve positive. So essentially, it's insensitive to how much is produced, as over time, this is the cosmic scale factor. They will always approach a scaling solution. So the detail of production is not important because the scaling solution depends only on the very non-trivial behavior of string theory. And one reason clear, if you produce a lot of strings, they tend to chop each other off, and then with the loop, they decay rapidly. If very few strings, remember we said it goes like 1/a², so you will be more important as evolved. So the two balances itself to give a scaling solution. And unfortunately, a lot of numerical work have to go into it because typical cosmic string network involve multi-scales. Scales from tiny strings to size of universe. And this is as multi-scale as possible. And even though this is classical problem, it's rather difficult to do analytically. Okay, so other properties which I have no time to go through, I just briefly summarize. The superstring loops are always closed strings in the same sector as gravitons. Of course, there can be long strings that stretch across the horizon, but there would be very few. And they evolve, strings in different throws evolve differently, so you start adding them up. And loops may emit axions because for string theory, there's always an axion associated with a string, and this may decrease with curly G. And of course, there's more complication in this. And the other thing is that we said they sit at the bottom throat, but they don't have it. They're oscillating at the bottom throat. And as they oscillate up a little bit, the warp vector is different, and the tension is different. So it's possible that you detect cosmic strings where along the line of along the string, the tension is different. Or you can look at pace, and over time, the tension will change. Okay? And by seeing this kind of oscillation behavior, that's a very distinctive property of cosmic string as well. So let me summarize the two key points I want to make, which one of them I did not say yet. So we have said that the superstring density is a few order magnitude bigger than cosmic strings. And in the plot I will give you for the case 100. Now, there's another very interesting property, because the tension now is very low. Earlier on, when the tension is G mu equal to 10 to the minus 6, 10 to the minus 7, the radiate gravitationally is proportional to the tension. The tension is high, they radiate quickly, they decay fast, and they essentially disappear. Now we talk about cosmic string tension is low, say 10 to the minus 12. Okay? If 10 to the minus 12 means that once you form the loop, they decay slow. Okay? They will live a long time, and if they live for a long time, it also means that the relativistic motion that produced will be damped by the expansion universe, so they will become relatively non-relativistic in terms of overall motion. Once they are slowed down in motions, and if the strings loops are smaller than galaxy size, they will behave more like dark matter, and they will clump or cluster like dark matter. Now we know that dark matter in the galaxy is much bigger than the dark matter density outside in general, and to the best we can estimate, the dark matter density in our galaxy is 5 orders magnitude bigger than the general density in the universe. That's where all the clumping, clustering happen. Now, for cosmic superstrings, we find that the same behavior happens if the tension is lower than 10 to the minus 10. So if the tension is above 10 to the minus 10, they don't have time to be damped to become like the non-relativistic dark matter. However, if the tension is 10 to the minus 10, 10 to the minus 11, then more and more of them can be damped and behave dark matter and clump. And when you get to 10 to the minus 12, you can get an enhancement of 3 or 4 magnitude. And the tension goes to 10 to the minus 14, you get 5 order magnitude. So this means that within our galaxy, the number density of cosmic superstrings is much higher than the earlier number people have. And that enhances the probability of detection. So we get a factor maybe 100 here, maybe a factor of field up to 5 order magnitude here. And that are the two effects that allow us to believe that the good chance to be measured. So here's one example I have. We take G mu equal to 10 to the minus 12. And this is the rate of event rate per year. So here means that 1 per year. Here means 10 per year. Here means 100 event per year. And this is the signal to noise. Okay? So at 0 means that signal to noise is 4. And then here signal to noise 40. And all the way up to like 200. Okay? This is signal to noise. And in this plot, I show a number of curves. So first I show the curve, which is ordinary cosmic strings will have. It will be the blue dashed line here, blue dashed line. So means that even if you're willing to sacrifice signal to noise, you get no more than 1 event every 10 years. Which is not observable. But if you now increase the Curly G factor of 100, we got this dash curve. And now we talk about clustering effect in our galaxy, we get this solid curve. So the solid curve will say that, well, if signal to noise is 10, we may still get dozens of events a year. This is before the upgrade of LIGO we use. And so things may get better over time. And we can even reach 10 to the minus 14. So this is why we believe LIGO has a chance of detecting cosmic superstrings in the near future. LIGO, of course, I mean, integrating Virgo and Kagra will give you further improvement. And Lisa, of course, will do better. I didn't even show that, so Lisa's future. So this was 10. The other way is that if you have a cosmic string in front of star, then there's a deficit angle, and the star will appear as double image. Okay? So that means that this is double image as a string move past, and further out, then it would be go back to single image. So you have a single image, and as a string move across it, it becomes double. And that means that we cannot resolve it, but we see double luminosity. So this offers a chance that we can detect it by looking at the varying luminosity. So typical string move around, will oscillate, and then the whole string will move. So you may see something like this. This is luminosity of a star in general. And this is when the cosmic string moves past it. So it would be very digital, and then repeat again. So this pattern would be very clear. Now, of course, exoplanet actually surge and change the luminosity by 1 pi to 100,000. And if that's the case, we can reach G to 10 to minus 18. So together of this gravitational detection, together with microlensing, and since that we're looking mostly, hopefully, within our galaxy, so there's a lot of stars behind, that this offers a chance of detecting it. Obviously, finding strings in string theory probably is the best possible evidence you can have. And we hope that people look for it, and that together with microlensing, two can go together, and that should offer strong evidence of detection in the future. And microlensing at this moment is going on. It's not so easy because you need to look at many stars before you have a chance to see one which has a string just moving in front of it. But LSFT, with W first, we think that they have a good chance of detecting some of them. So, okay, thank you.
Thank you for a nice talk on the string in connection to gravitational detection. Questions?
So I was confused about something very basic. So you're in your throat, we live on some stack of D3 brains, and these strings, are they bound to these D3 brains or not?
Okay. This is an issue that I didn't go into. If there's cosmic string in the bottom of the throat with D3 brain, then the fundamental string will break up because open string can live there. So fundamental string cannot be cosmic string. The D strings, on the other hand, will pick up some width, but they are metastable, so they, as far as we can tell, they can live for a long time. And they will be the only cosmic strings we have. And they will look very much like vortices. However, we have many throats. Inflation may happen in different throats, and the energy released there can propagate to various throats. And so each throat will have its own cosmic string network. Depending there's brain or anti-brain, D3 or anti-D3 brain sitting there, we will have D and F strings or only D strings. And each of them will evolve independently to a scaling string network. That's a multiplicative factor. Depends how many throats we have tension big enough to be observed.
But are they bound to our stack of brains, or do they propagate freely in the throat?
Oh, yeah, that's a good question. It's possible that we have stacked D3 brain, so it depends. If it's conical, of course, that's only a point. But you can deform the conical so that there's a space. Can D3 brain sit here, cosmic string can be close by, then they are not bound. They are essentially close string there. But my gut feeling is that the strings will hit the brain and will disintegrate for the F strings.
Okay.
Notice you mentioned Tye2 and Tianjin, these two projects. So what's the, do you know some inside story in the current situation?
I think Tianjin is a long way. Okay. And Tye2, well, let me describe LISA. It's more important. So LISA used to be with US and then become E-LISA with only Europe. And now, recently, in the last few weeks, European Space Agency have decided to go ahead no matter what. And they go back to the LISA project. So it's no longer E-LISA. That's why I dropped the E. You know, I don't have the E, you notice. Okay. And because now the E-LISA project, go back to the LISA project with 3, and they're going to go ahead no matter what. And furthermore, originally they planned in 2035 to launch. Now they try to move up to 2028, if possible, and fully funded. So the only unknown is that what's the distance between the 3 detectors. They're so successful with Pathfinder, they're talking about between 2 million to 5 million kilometers apart.